Special case, sum of the first n positive integers. Welcome back, everyone. In our previous lessons, we spent quite a bit of time exploring the general formula used to find the sum of any arithmetic progression, or AP. Now, while that general formula is incredibly powerful, today we are going to focus on a very special case. In mathematics, we very frequently encounter a specific scenario where we need to find the sum of the first in natural numbers, which are simply our positive integers. If you look at the sequence of numbers starting from 1 and increasing by 1 each time, you'll notice that this is actually the simplest, most fundamental form of an arithmetic progression. Because this specific type of sequence appears so often in both math problems and real-world applications, mathematicians have developed its own simplified formula. This means that instead of using the longer, more complex general formula we just learned, we can use a much quicker shortcut. In the next slide, we'll break down exactly how this sequence is structured so we can see why this shortcut works. Understanding the sequence. The sequence of the first n positive integers is simply 1, 2, 3, 4, and so on, all the way up to n. Now that we know we are looking at a special case of an arithmetic progression, let's take a closer look at what this specific sequence actually looks like. To use the formulas we've learned previously, we need to identify the key components of this specific sequence. First, let's find the first term, which we represent with the letter e. Since our sequence begins with the number 1, our e equals 1. Next, we need to determine the common difference, which we call d. If you look at how the numbers progress, each term increases by exactly 1. For instance, 2 minus 1 equals 1, so our d is also 1. Finally, we need to know the number of terms we are dealing with. Since we are summing everything from the very first number up to the nth term, the total number of terms is simply n. Keep these values in mind, because in the next slide, we are going to plug them into our general formula to derive a much simpler, much faster formula just for this type of sequence. Derivation of the simplified formula. Now that we have identified our key components, the first term, the common difference, and the number of terms, let's see how we can arrive at our new simplified formula. We don't actually need to memorize a brand new rule. Instead, we can derive it using the general arithmetic progression formula we learned in our previous lessons. Let's walk through this derivation step by step. First, we start with our foundation, the general formula for the sum of the first n terms. This is written as S sub n equals n divided by 2 multiplied by the quantity 2a plus the quantity n minus 1 times d. Next, we perform the substitution. Remember from the previous slide that for our specific sequence of natural numbers, our first term, a, is 1, and our common difference, d, is also 1. So we replace a and d in our equation. Now the equation looks like this. S sub n equals n divided by 2, multiplied by the quantity 2 times 1, plus the quantity n minus 1 times 1. Now let's move to step 3, where we simplify the expression inside the brackets. When we multiply those terms out, the equation simplifies to S sub n equals n divided by 2, multiplied by the quantity 2 plus n minus 1. In step 4, we combine the constant numbers inside the brackets. Since 2 minus 1 leaves us with just 1, our expression becomes much cleaner. S sub n equals n divided by 2, multiplied by the quantity n plus 1. Finally, in step 5, we arrive at our final simplified form. We can write this as S sub n equals n times the quantity n plus 1, all divided by 2. And there you have it. This beautiful, compact formula allows us to calculate the sum of the first n positive integers instantly, without the need to perform the full, more complex AP calculation every single time. This will be incredibly useful when we look at practical applications, like the crate stacking example coming up next. Real-world application. Now that we have derived our special formula, let's see how it actually works in a practical, real-world situation. Imagine you are a warehouse manager, and you are tasked with stacking crates in a triangular pile. To keep the pile stable, you place just one crate on the very top row. The second row directly underneath it has 2 crates, the third row has 3, and this pattern continues all the way down until you reach the 20th row. Your goal is to find out exactly how many total crates are in this entire pile. Let's walk through the solution step by step. First, we need to identify the information given in the problem. If we look at the number of crates in each row, we see a sequence of 1, 2, 3, and so on, up to 20. This is exactly the type of sequence we just studied. Since we are counting from 1 up to 20, the total number of terms, which we call n, is 20. Second, we need to choose the right formula. Because our sequence is simply the first 20 positive integers, we don't need to use the long, general arithmetic progression formula we saw earlier. Instead, we can use our new simplified formula. S sub n equals n, multiplied by the quantity n plus 1, all divided by 2. Third, let's substitute our value into the formula. Since our n is 20, the equation becomes S sub 20 equals 20, multiplied by the quantity 20 plus 1, all divided by 2. Fourth, let's perform the calculation. Inside the parentheses, 20 plus 1 gives us 21, so we have 20 times 21, all divided by 2. To make this easier, we can divide 20 by 2 first, which gives us 10. Now, we just multiply 10 by 21. This brings us to our final answer. The total number of crates in the pile is 210. As you can see, using this special case formula is much faster than adding every single number one by one. Key takeaways. First, it is important to remember that the sum of the first n positive integers isn't just a random rule. It is actually a special case of the arithmetic progression we studied earlier. Specifically, it's what happens to an AP when the first term, which we call a, is equal to 1, and the common difference, which we call d, is also equal to 1. Because of this specific setup, we don't need to bother with the long, complex formula every time. We can use this much more streamlined, simplified formula. S sub n equals n, multiplied by the quantity n plus 1, all divided by 2. As you saw in our crate stacking example in the previous slide, using this version is significantly faster and more efficient than plugging everything into the general AP formula, provided your sequence starts at 1 and increases by exactly 1. All right, let's wrap up what we've learned today by looking at the key takeaways. Now, before we finish, I want to point out a few common pitfalls to watch out for in your future problems, so let's take a look at the next slide. Common mistakes to avoid. First, be very careful about applying this simplified formula to non-consecutive integers. I have seen many students try to use n times, n plus 1, all over 2, for any arithmetic progression they encounter. Please remember, this specific shortcut only works if your sequence starts exactly at 1 and increases by exactly 1, like 1, 2, 3, and so on, up to n if your sequence is something else. For example, 2, 4, 6, and so on, or perhaps 5, 10, 15, you cannot use the shortcut. In those cases, you must revert to the general formula we discussed earlier. N over 2, multiplied by the quantity 2a plus n minus 1 times d. Second, watch out for using the incorrect value for n. It is vital to ensure that n represents the total number of terms you are actually adding up. For instance, if a problem asks you to find the sum of integers from 1 to 100, your value for n is 100. Don't let the range confuse you. Always count the total number of terms in the sequence. Finally, keep an eye on your calculation steps to avoid simple arithmetic errors. A common mistake is to multiply n by itself and then try to add 1 to that result. To stay accurate, always follow the proper order of operations. First, calculate the quantity of n plus 1. Then, multiply that result by n, and finally, divide the whole thing by 2. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even when you understand the concept, it is very easy to make small errors that can lead to the wrong answer. Let's look at some common mistakes to avoid. If you keep these 3 points in mind, you'll be well on your way to mastering this special case of arithmetic progressions. Great job today!